Light travels so fast, bends around corners, and bounces off mirrors just like we'd expect. But what if I told you there's an exotic state of light that slows down to mingle and flow in unison? That's right. Researchers have discovered that in certain circumstances, light can behave like a liquid. And you can see it for yourself in this video. This isn't really light acting like a liquid, but the way the photons interact with each other is similar enough to earn the title liquid light. It's like how people sometimes call black holes star stuff, even though they aren't stars. Anyway, let's get into it. Most folks think there are only 3 states of matter: solid, liquid, and gas. We learned about that in grade school. But actually, there's a 5th state called a Bose-Einstein condensate, or BEC. In this state, particles act like a single superparticle, almost like they're a living single cell. So the question is, how can light act like a living cell? Well, turns out it can under the right conditions. You see, light has a dual nature. Sometimes it acts like a particle, and sometimes it acts like a wave. When it's a particle, we call it a photon. And when it's a wave, well, it's a wave, and all waves have a wavelength. The color of light tells you its wavelength. Red light has longer wavelengths than blue light. But white light contains all the colors and therefore all the wavelengths. Now here's where things get weird. Usually those wavelengths are all jumbled up and look like this. But if you take 2 of these jumbled up sets of wavelengths and combine them together, something interesting happens. The result looks like this. Yep, it's kind of like a wave. That's because the wavelengths of the 2 sets of light overlap and reinforce each other. This is called interference. It's the same reason why oil slicks have those cool rainbow colors. The light waves reflecting off the top of the film interfere with the light waves that go through the film and out the bottom. Where they interfere constructively, the light is bright. And where they interfere destructively, the light is dark. Now this interference only works when the wavelengths are similar. If the wavelengths don't line up, then you don't get this kind of interference. But here's the kicker. Photons also have momentum and energy, and the shorter the wavelength, the higher the energy. So in a gas of photons, the shorter wavelengths bounce around, giving the longer wavelengths a little bit of their energy, causing the wavelengths to blur together until they're all the same. So the whole thing becomes a single wave instead of a bunch of different waves. This is the Bose-Einstein condensate of light. So the key to making this work is temperature. You need to get the temperature down close to absolute 0 or negative 273 degrees Celsius. At that point, the wavelengths blur together and act like a single wave. At everyday temperatures, the wavelengths of light are just too spread out to do this. So it's basically impossible to make a beck of light at room temperature. But researchers did something clever. They used a gas of rubidium atoms which also have a wavelength. They cooled the gas to a BEC by blasting it with laser light. Then they took a second laser and shot it through the cloud of rubidium atoms. The photons in the laser gave most of their energy to the atoms and slowed down. Then the rubidium atoms re-emitted the light as a coherent beam. Essentially, they took the rubidium atom's wave and turned it into a photon wave. And now get this, the rubidium atoms went back to their normal state because they gave away all their wave-like properties. So now you have this beam of light that's moving in unison like a single wave. Researchers could even split the beam into 2 and recombine them, and it still acted like a single wave. But wait, atoms can also act like a wave. Why not turn the rubidium atoms back into a BEC? Turns out they already were. Remember, beads act like a single particle. So if you shine light on a bake, it'll absorb it and act like a single big atom. And that's exactly what happened. The entire BEAs absorbed the laser light and re-emitted it as a single photon. They confirmed this by splitting the beam and recombining it just like before, and seeing that it still acted like a single wave. In other words, they took a bunch of rubidium atoms, turned them into a BH, shot a laser through it, turned the rubidium atoms back into a regular gas, and got a laser out. Now this doesn't prove that light itself can be a BK. That would require cooling light all the way down to absolute 0. But it's pretty darn close. In fact, physicists have created a BEC of light in 2001 by shining a laser on a cloud of cesium atoms at a temperature of just 4 nanocelsius above absolute 0. But that method required a lot of power and it wasn't very stable. So while we know BECs of light are possible, it's still easier to work with the rubidium atoms. So what does this mean? Well, BECs of light have some potential uses in things like quantum computing and cryptography. And understanding BECs in general helps us understand the universe at a fundamental level. BECs were predicted nearly a century ago by the physicists Satyendra Nath Bose and Albert Einstein, but the first one wasn't created until 1995. Now we're getting better at creating BECs and at lower and lower temperatures. Who knows? Maybe someday we'll be able to create one at room temperature. If you liked this video, check out my last video about how gravity affects the quantum world. We had a ton of fun making this video and we hope you learned something. Thanks for watching.